Good morning, everybody. Happy snow day. Today we're just going to go through a lecture up through bond energy, hopefully, and then your homework is really just the homework you were given over the weekend, so nothing additional, but hopefully the lecture will help solidify maybe some areas where you were a little confused. Please remember that the vocab quiz will be tomorrow when we return to school on Tuesday. Also, any background noise you hear, if you hear my kids yelling at each other or something when they get up, but hopefully that won't happen or me yell at them. Okay, so here we go. I can't remember exactly. I think our two periods are at a little bit different spots, but in a nutshell, we were looking at polarity. We were looking at bond polarity and also molecular polarity. So here we've got symmetrical molecules. Last year we talked about tetrahedral, trigonal, planar, and linears being symmetrical molecules. That sometimes those are polar molecules and sometimes they are not. Here's a case of carbon dioxide where we have a molecule here that's got two polar bonds from the carbon to the oxygen. But because of the symmetry of the molecule and that with these bonds, even though the electrons are being pulled away from the carbon by each of the oxygens, because of the locations of those oxygen atoms, they kind of offset each other on their pull, and the overall molecule is considered nonpolar. And so when you have symmetrical shapes like the tetrahedral, the trigonal, planar, and the linear, you are looking at the external atoms, the outside atoms, to see if they are the same. So we've got an O here and an O here because their electronegativities are identical and their pull is opposing each other. The whole molecule ends up being symmetrical. Okay, so here's a chart. Okay, maybe not, and then we'll see it in a minute. Here's a couple of other molecules. We've got HCl here. We have just two atoms in that molecule, and they both are different, so their electronegativities are different, and one atom pulls more than the other. So we do have a dipole moment in this molecule, the electrons being pulled towards the chlorine here. And then this molecule here, SO3, I think this was in a homework problem that you had. This is trigonal planar. The outside atoms are all identical, so the pull of the electrons from the sulfur is equal and counterbalanced around that three-dimensional atom there, or molecule there, and so that ends up being a non-polar molecule, even though it is made up with somewhat polar bonds, whereas the top one up here, this linear shape, is not symmetrical, and you can tell by the shape of that dipole there, cloud. And then over here we have methane. This time the electrons are being actually pulled towards the center of the molecule because carbon has a slightly higher electronegativity than hydrogen. But these bonds are considered nonpolar. Any CH bond is considered nonpolar. And even though that pull is going towards the carbon, because that is a symmetrical molecule and all these outside atoms are identical, then that is a nonpolar molecule. Here we have a bent structure with sulfur pulling the electrons in both of those hydrogen bonds more than the hydrogen, so you can tell by this diagram here with the colors that there is an offset in electrical valence on that molecule, and so that's a polar molecule. And the center of positive would be right up here between the hydrogen, and the center of negative would be centered over that sulfur. Okay, now we're talking just a little bit about ions. And you know what ions are. I'm not going to go through all that, but I do want to touch on what the sizes are of ions and the trend for those. Before we do that, let's talk about this scenario here, and this is going to be something that you're probably going to have to do, and that is to predict the formula of an ionic compound using the electron configuration. So you've probably done it before by looking at calcium, finding its charge, oxygen, finding its charge, and figuring out what ratio you need of those ions to make the compound neutral. But you also need to understand what's actually going on here with the electrons in the arrangement. Remember, ions are trying to achieve an outer valence shell of 8 electrons for the most part, except for those transition metals. So here we have the configuration of calcium, excuse me. It has these 2 valence electrons. Oxygen has 6 valence electrons. Both of them would like to have those 8 valence electrons, which is a stable situation for them. So you see here that calcium wants to lose these 2, will lose these 2 because it's a metal, it gives up electrons, and oxygen is a nonmetal and it likes to gain electrons. So these 2 electrons here can go and fill out this valence shell for oxygen, which would then give it 8 valence electrons, and it only takes 1 calcium to donate those 2 electrons to complete that outermost shell here on the oxygen. So by looking at the electron configurations, it's important for you to be able to predict what that compound chemical formula would be. It only requires 1 calcium and 1 oxygen for each of those to fulfill its octet rule there. And then here's just a balanced equation to kind of show you what's going on here. They exchange the electrons, and then after those ions are formed, then those ions attract towards each other, making that ionic bond and that ionic compound. Okay, so then this is a chart that just has a lot of the common charges that you'd see, so you're familiar with that. Now looking at the trend in size of ions, for atoms, the trend is it gets smaller as you go left to right, and the size gets larger from top to bottom. Similar pattern with ions, but slightly different. When you look at the trend for the ions, you have to divide the ions from the metals to the nonmetals, okay? Because if you look straight across in the periodic table, if you can follow here, if you go across, yes, the ions get smaller and smaller, but then when you reach those nonmetals, you get a huge jump in size. So when you are comparing sizes of ions, you do need to divide them to metals and nonmetals. They both have the same trend, but the trend does not continue across the table. So yes, the positive ions do get smaller as you go across. Then there's a big jump when you get to the negative ions, and then as you read from the negative ions across, they do get smaller as well. And then you go top to bottom, the trend is the same as atomic size. You notice that it is increasing as you go down based on those energy levels being added. Here it is based on the effective nuclear charge, but here, when we get to the nonmetals, we are gaining electrons, and so you've got more electrons in that same sublevel, and so the repulsions are larger, and so the ion gets larger when you do add electrons to those. So in essence, it's fairly safe to say that the cations become about half the size of the parent atom that they come from, and the nonmetals, the anions, become about double the size of their parent atoms. It's fairly safe. Of course, it's not exactly that, but it's fairly safe to say that. So little rule of thumb, I guess you can go by for that. And then the other thing that we need to talk about is something called isoelectric ions here. All right, and so what we're talking about here, iso meaning same, electric meaning the electrons. So these are ions that have the same number of electrons, but they have different number of protons, and that's where this Z comes in. Remember, the Z number is the number of protons that we're talking about, and they call that nuclear charge. You're familiar with that. Now, when you have an isoelectric series, that's ions that all have the same number of electrons but different number of protons. As the number of protons increases in that series, the size decreases. So there's an indirect relationship between the Z number or the atomic number and the size when you're looking at an isoelectric series. And that's what this is saying here, this inversely proportional to. So keep that in mind. So here I think we've got an example. These are isoelectric series. If you look at your periodic table, all of these ions here hinge around, let's see, the krypton electron configuration. All right, so all 4 of these ions have the same number of electrons, but as you go from left to right here and becoming more positive, you are adding more and more protons to the nucleus. Therefore, those protons are pulling more tightly on those same number of electrons in each of these. So the selenide ion would be the largest of these. The bromide would be the next largest, rubidium, and then strontium would be the smallest here. So you need to keep that in mind. And this is once again called an isoelectric series, when you have those ions with the same number of electrons. Okay, then here we're just looking at these ions here in letter A. Those are all found in group 1 on your periodic table, so you should know that as you go top to bottom, the size gets larger. And then when you look at the periodic table here and compare your barium, cesium, iodide, and your telluride ions there, they are all have the xenon electron configuration. So this is your isoelectric series here, and they are going to be what did they want? Choose the largest ion. So that would be the one with the fewest number of protons. So that would be your telluride ion there. So I hope that makes sense. Okay, now what we're going to do is look at lattice energy and how that interplays with the energy associated with forming an ionic compound. All right, so lattice energy is basically the energy that is released when two gaseous ions come together to form an ionic solid. So you see that here in a general equation. We've got M ion, which is basically standing for metal in its gaseous state, and the X is representing the nonmetal ion in its gaseous state. And then the energy associated with those two things coming together, attracting each other and forming a solid is called lattice energy. Now what we're going to see the use of lattice energy in a couple different ways, but the first way is to see how we can incorporate lattice energy into basically an enthalpy problem where we can find the energy of a reaction using that lattice energy in addition with other energies to find the energy associated with the formation of a solid. So this example here, we're looking at the formation of lithium fluoride solid from lithium, elemental lithium, and elemental fluorine, well, molecular fluorine. And to do this, we are going to incorporate that lattice energy. And what we have to keep in mind, you had a couple problems in the back of your chapter that we're dealing with this. Keep in mind that in order to incorporate lattice energy into this problem, both of these species here have to be in the ion form and the gaseous state. And you'll notice neither of these are in the ion form and only one is in the gaseous state. So what our goal is to convert these species into that form. And in order to do that, there's energy associated with converting lithium to a gas and then into an ion, and then converting fluorine into an atomic species and then ionize it. Then we will incorporate the lattice energy into that. And we're really using Hess's law as we're doing all of this. So if you just kind of follow along here, hopefully it'll make sense. So the first step that we're going to do is take the lithium, which is in its solid state, and we need to make it a gas. So that is going from a solid to a gas is sublimation. So that's what you see here, and there's energy that's required to do that. So this is the energy required to do that. You would be given these values. You do not have to know these values. Maybe it will be given in a table form, but somehow in the problem they will provide this information. You just need to assemble basically all the parts to make the sum to find the sum of all of this. So here we've got our lithium subliming, and that's going to require 161 kilojoules. So we're going to take that number and add to that all these subsequent energies to convert these species into the form needed to use lattice energy. So then the next thing we need to do is take that lithium gas now, and we need to ionize it. Now we're taking a metal and ionizing it is removing an electron or giving off an electron. So that's ionization energy. So that's why that is written here, and it takes 520 kilojoules per mole to remove that first electron. So now what we've basically done is by these two steps, we have converted lithium into a gaseous state and an ion form. So it is in the form that we are able to use in our lattice energy. So we're going to add these two numbers in the end along with a couple other ones. Now we're going to look at fluorine. It's kind of come off the screen at the bottom here. I apologize. And we need to take the fluorine, which is up here, and we need to make it atomic instead of diatomic. And to do that, we need to break that bond. Now, keeping in mind that when you do that, the energy that was given for this is actually taking F2 and breaking it down into 2 fluorine atoms. Okay, that's the energy that's provided in the textbook for that. And I think that energy was, let me find it here. I think it was 154. So it's 154 kilojoules per mole to do that. But if you look at the equation up here, we actually have half a mole of fluorine to break that apart. So what we've got down here in the bottom of the screen, you see we've got that half a mole of fluorine converting to just a fluorine atom. So we're going to have to take this and we're going to have to divide it by 2 when we do this particular step, because we are dealing with half a mole, not 1 mole. And that ends up being 77 kilojoules per mole. So that's where this number comes from. So then the next step we need to do, now that we have our fluorine in an atomic form instead of molecular, the next step is we are going to ionize that fluorine atom. So that means we're going to gain an electron. If you all remember, that's electron affinity, even though they don't have it written that way right here. This actually is electron affinity. And the electron affinity for fluorine is negative 329 kilojoules per mole. So these are all the different energy steps that need to be taken. What we've essentially done is converted, if I go back here, lithium into the lithium ion in the gaseous form and the fluorine into the fluorine ion in the gaseous form. And then what we can do is incorporate the lattice energy of taking the lithium ion and the fluoride ion, forming it, those bonding and making the lithium fluoride solid. And the lattice energy for that particular substance is negative 1047 kilojoules. So we're going to take all of those energies that we looked at in step 1 through 5, and we're going to add them together. We're summing them. Signs are important. Carry those through as you do that. And then you will get the energy associated with the change of lithium solid and fluorine, half a mole of fluorine gas into the lithium fluoride. So here are all the individual steps that we were looking at before. All right, the kilojoules are up here, and then we are adding in all those individual steps, and in the end, we get this overall equation. Again, really the underlying factor here is we're using Hess's law, and then here is our final energy that's, in this case, given off, which you would expect when ions come together to form a solid. That energy would be given off. Fairly exothermic. For that, we know it's exothermic because we have that negative sign there. So here is another way to depict the similar problem using what we call an energy diagram. So each of these individual steps are what we saw before. Steps 1 through 5 are depicted here, but using an energy diagram. Okay, so we had a couple of steps that were endothermic, actually 3 steps here that were endothermic. We had 2 that were exothermic, and then the overall or the net change on this is this 617 kilojoules. So it is exothermic for the formation of that lithium fluoride crystal. So you have a couple of problems in the back of your chapter that you were doing with those. That's one of the type that you'll have. Another type you might have is, let me step back here. Okay, so here were all the steps we added together. Occasionally they will give you the total. And all of these up here, except for maybe one, and that would be x, and then you would solve for x. So that's just another little variety they may give you for that. Okay, yeah, I think that was number 57 and 61 are the 2 that you actually have to do calculations with. And there's another type of lattice energy problem that actually involves Coulomb's law. So let's take a look at Coulomb's law and how that applies. Okay, let's look at this picture first. So here we've just got a crystal structure of that lithium fluoride. Again, the thing you need to keep in mind when you think about ionic compounds is that it's just an alternating array of positive, negative ions, positive, negative ions, positive, negative ions, this big network here of all those ions, and it is alternating positive, negative, otherwise it would not be stable, and that's one reason why ionic compounds are fairly brittle. You apply some force to this and it shifts those ions out of their pattern, and then you've got repulsions taking place there that are not what the ion wants to do, the ions want to do, and then that will cleave at those spots and then it'll break apart. So that's one reason why ionic compounds are brittle. But these attractions are very strong here, and the melting points and boiling points of these substances are extremely high. And that is really how we classify something as ionic compound, is by once that substance is melted, they try to conduct electric current, and if it does conduct electric current, then it's classified as an ionic compound. Here was a neat crystal that was formed a couple years ago from that beginning of the year lab. I just thought it was really cool when these ladies were letting their water evaporate. There must have been a small seed crystal in here, but this is just sodium chloride, and it's great because it shows you that that actually is a cubic structure there. And I think that's kind of neat. It just happened all on its own. We didn't actually add a seed crystal to that. It just went on its own and did that. So it's kind of fun to see things like that happen. All right, so then here's another application of lattice energy using Coulomb's law. This is a modified form involving ionic compounds. What we're going to be focusing on is the top here. Q1 and Q2 are your charges of your ions. And notice that they are multiplied by each other. So the larger the charges, the larger the lattice energy. And then we've got the radius in the bottom, and that's basically talking about the size of those ions. So the smaller the size of the ion, the larger the lattice energy will be. So those are a couple of things we need to keep in mind if we look at a situation like this where we have SRO and SRBR, and we are asked to tell which of these compounds would have the greater lattice energy. The first thing you want to do is look at the charges of these ions. So this SR is a 2+, the O is a 2-. Here in this compound, again, we have a SR is a 2+, and the BR is a negative. Now looking at Coulomb's law over here, the greater the magnitude of the charge, the larger the energy. So 2 times 2 is 4, which is much larger than 2 times 2. It's double that. So you would probably expect the lattice energy involved with the formation of this compound SRO to be maybe double the lattice energy of SRBR. So you do have a couple problems at the back of your chapter where you're rationalizing the trend in lattice energy, not trend, but the ionization energies, or picking which compound has a higher or lower, greater or smaller lattice energy. So the first thing you're going to do is look at the charge of the ions in that substance, and then the one that has the larger magnitude of charge will be the one with the larger lattice energy. If you have a situation like this where you have SRO, that R in there, it's a cruddy R. And then we've got MgO. Did I do that right? Yeah. In this case, both of these have the same magnitude of charge because this is a 2+, this is a 2-. Here we've got a 2+ for the magnesium and a 2- here. So the magnitude of charge is the same for both of these. So we cannot look at charge as determining which one would have the larger or smaller lattice energy. Now we have to look at size. Well, the O's are the same ion, so their size isn't going to be the impacting one, but the strontium and the magnesium, this is driving me nuts. There we go. The strontium and the magnesium are different sizes, and you've got to look at your trend on the periodic table, and you should notice that magnesium is nearer to the top than strontium. So this is the smaller of the ions, and what did we say? The smaller the size, the larger the lattice energy. So comparing these two compounds, if we were looking for the one with the larger lattice energy, that would be the magnesium oxide due to the smaller size of that magnesium. The closer those ions can get to each other, the more energy that's going to be released by that. But and this comes up here in our little wording that's going to come up here, give it all that crud on there. So it says here that when you are comparing different compounds and trying to predict which would have the higher or lower lattice energy, this is what you need to do. First of all, the magnitude of the charge is the dominant factor. You're going to look at that first. And then if those happen to be the same, then you're going to look at ion size. Okay, so this would be number 1. Focus on that first. And then radius would be number 2. Weird 2. And then here again, the smaller the size, the larger the energy change. All right, so that should pretty much take care of our lesson on ions, I think. Let me double check here. Okay, this one is talking about the comparison of NAF and MgO, and you should have read that in your textbook. I'm not terribly worried about that one. Okay, yeah, so we are going to move on here and start talking a little bit more about covalent compounds here too. I'm at almost 25 minutes, so I gotta get moving. All right, so here this is talking about bonds that are partially ionic in character, which basically means they're in that polar region of our scale of 0.4 and less, and then the 2.0 and greater. We're looking kind of at those polar ones. But there is a way that scientists can classify bonds as polar or nonpolar based on a calculation, and this is the calculation that is done. You are not going to do this, but just gives you an idea of where this next chart comes from. They measure the dipole moment, and then they can calculate the dipole moment, and they compare those two values, and then they get what they call a percent ionic character. So what this chart is doing, notice it's graphing percent ionic character on the Y and the electronegativity difference on the X. And again, sometimes you'll see that written as delta En. That's another symbol for electronegativity difference. Notice here's our 2 cutoff, right? We were talking about before 2 and greater is ionic, and then before we said 0.4, which would be just about here, maybe-ish, Noah. And then here is the nonpolar and less. So these are all other ones that would be considered nonpolar covalent. However, these, if we simply looked at metal and nonmetal, we would classify all of these as ionic. So there are ways that they can kind of look and say, well, this is more ionic in character than another. And then here you see the lithium fluoride. The fluorine is that highly electronegative element, so you notice that those seem to be a little bit more ionic in character, etc. So just kind of an interesting chart here. Notice there really isn't anything right up here at 100% for ionic in character. I don't know if there are any that are truly 100% ionic in character, whereas there are truly some molecules that would have that 0% ionic character. Those would be your diatomic elements, hydrogen, chlorine, bromine, all of those diatomic elements. All right, so enough said about that. These are the different types of bonds that we have talked about last year, and we'll make sure we talk about this year. So this would be your nonpolar covalent bond, where you have the same atoms bonded and the electronegativity difference. The electrons are basically distributed evenly throughout the molecule. Here we have our polar bond, 2 atoms different. We talked about that a little bit at the beginning of the lecture. And then here we have our ionic. And again, the way they truly can classify whether something's ionic or not is by melting that substance, running an electric current through it, and seeing if it will conduct a current and light that light bulb that we looked at last year. And I think there's a picture here of that. So this is kind of the true test of whether something's ionic or not. Okay, so, and you've seen that. Of course, my electrical conductivity device is ancient compared to that one, but it doesn't matter. It works the same. Okay, so now we're going to talk about covalent bonds a little bit and bond energy, which is also another way that you can find the energy of a reaction. Some classes put this in with the thermochem area. I just leave it here with the bonding. I just think it makes sense to have it here. So what is a chemical bond? It's a force that causes the atoms to behave as a unit. Okay, remember when you break bonds, it requires energy. When bonds are formed, energy is given off. Okay, remember a bond is going to result when they've sought that lowest energy state. We looked at that way at the beginning of the chapter with the hydrogen molecule. Okay, so another way to look at that is when CH4 is formed, 1,652 kilojoules of energy is released when 1 mole of that is formed, which also means that it would take 1,652 kilojoules of energy to break those bonds and put them back, make them be in their atom form. Okay, so that means that they would prefer to be in the bonded form than in the atomic form because energy is required to do that. Okay, so that's what that was talking about there. Now, the bond energies that we're going to be using in our calculations are what we call average bond energies. So I want to talk just a minute about that. We said before that that CH4 molecule had energy associated with it of 1,652 kilojoules per mole. Okay, now there were 4 CH bonds in that molecule. So if we take the 1652 here and divide it by 4, we can find out the average bond energy for a CH bond, and it would be 413 kilojoules per mole. And all of the bond energies, like I said, that you're going to see on the table in a minute here are all based on this average. And the reason why they call that an average is, I'm going to skip ahead here just a minute here and find that slide, is that when you take this CH4 molecule and remove a hydrogen atom, the first hydrogen requires 435 kilojoules to do that. Then taking the second hydrogen off requires 453 kilojoules, not the same as the first one. And then the third hydrogen requires 425, and that last hydrogen 339. So to remove all of those hydrogen atoms is not an equal amount of energy each time. And that would just be a logistical nightmare if we had to try and figure out which hydrogen was being removed or which atoms were being broken, bonds were being broken, etc. So we always base it on an average. So if we look at all those individual bond requirements to remove those, we get that 1652 total, divide it by 4, and then we're working with an average when we do our calculations. So I did want to make a brief mention about that. Okay, going back here, some things that you can do with bond energy. I think this is the funniest looking molecule. Huge CL here and these little H's there. But anyway, so if we knew the entire energy associated with this molecule, okay, we knew the energy it took to break all those bonds, and I knew the energy for all of these bonds here, and it was that 413. I could take that total energy for the entire molecule and subtract the 413 kilojoules for each of those, and then I could solve for the energy associated with that bond. So that's one type of problem that may arise, and that's this one here. I'm really kind of going to go past this because I want to move on to some other things, but that's the underlying concept behind this particular example here, so you can read through that in your textbook if you haven't already. This is worth looking at, models. Talking about how models are so very important, but flawed. And it talks about why they're flawed. So please take some time to look at that. And that's one reason why we have so many different models, because they cannot cover every possible scenario. So interesting read there. I'd like you to do that. And then that was our bond energy one. Okay. Let's see if there's anything I need to say here. I don't think so. You can read through that. Now this table is one in which you'll be using. We'll refer to this as you're doing some of your problems, finding your enthalpy of reaction by using bond energies this time. So there's a few things I need to say about using this table here. First of all, notice if you are dealing with carbon dioxide, okay, notice the bond energy there for carbon dioxide is going to be different than the bond energy. So this bond energy here is for any CO double bond. But down here in the left-hand corner, if you're dealing with carbon dioxide, you're going to have to use this number here. So just keep that in mind. Okay, there's a little exception there. I honestly don't know why, but I just know that that's something we have to keep in mind. All right, so all these are covalent bonds. Now notice our lines. Our lines mean that those electrons are being shared. One line means a single bond, 2 lines means a double bond, 3 lines means a triple bond, etc. And then there's some things that we'll notice when we look at double and triple bonds and that kind of thing, but we'll talk about that later. These are all in kilojoules per mole, so notice your units. And then basically what you're going to be doing is finding the energy for a reaction by looking at all the different bonds that are involved in the species in that chemical reaction. And it's similar to what we did when we did standard enthalpies of formation, where we did the sum of the energies and then we subtracted the products, or subtracted the reactants from the products. So similar to that. All right, so let's kind of review a little bit. Single bonds, you have 1 pair of electrons, double 2 pairs of electrons shared, and triple 3 pairs. There's never going to be a quadruple bond. Notice here it says that as the number of electrons shared increases, the bond length shortens. So if you have a double bond, it's shorter than a single bond. If you have a triple bond, it's shorter than a double bond. Those electrons are being pulled tighter and tighter between those atoms. And a nice little visual for that I was going to show you in class with rubber bands, but we're not at school today. All right, here is that relationship. If you look at CC single, CC double, CC triple, look at what happens to the bond length. Those are picometers. That's what PM stands for. It does get shorter as those bonds are sharing more electrons. And then take a look at what happens to energy. What do you notice? I feel like Dora the Explorer. Can you find it? Back? Anyway, okay, so as those bond number of electrons that are increasing between those two atoms, the bond energy is increasing as well. The bonds are getting shorter, they are getting stronger, and it requires more energy to break them. That's one of the reasons God has surrounded us by nitrogen. Nitrogen is connected with a triple bond, and it is a very stable substance, so that when there are matches lit in the environment or what have you goes on, that we have molecules around us that are stable and not going to break apart very easily to protect us. So alrighty, so that's something you need to keep in mind here with those. You may be using these. I don't know that you're going to be using these. I think these are mainly just here to show you the trend and what's happening with those. All right, so what do we do with these things? As it says here, bond energies can be used to approximate the energy of reaction, basically. Okay, so here we've got a reaction. We want to find the energy associated with that. The basic idea with this is you're going to have to draw out the Lewis structures for these things, because you need to know what types of bonds are in the species so that you can select the correct bond energies. So please make sure you're drawing your Lewis structures. Don't get cocky and think oh yeah, I know what that one is, because there might be something you missed or you have forgot. These are both single bonds if you drew those out, and this one actually is single bond as well. But please don't just think, oh yeah, I know what that is. Double check, okay? So what you do is you go to your bond energy table, and you're going to look up the bond energies for all of the species that you've drawn out. You'll have an HH. Draw it real quick here. So this one, get these guys out of the way. Okay, so here you're going to have an H bond for that guy. This is going to be an F bond. I'm not going to draw all the little dots it should be. And then here you've got HF, but you actually have 2 moles of it. So keep that in mind. That's important as well. Remember, our enthalpy is an extensive property. It does depend on how much you have. So you look up the bond energy of the HH, you look up the bond energy of the FF, you look up the bond energy of HF and multiply it by 2 because you've got 2 moles. Now, the trick with bond energies, up to this point, I always said it's products minus reactants, right? That's what I've said in the past. That is not true with bond energies. When you're dealing with bond energies, it's always reactants minus products. Please put a red flag in your brain whenever you see bond energy and you have to do enthalpy, that is always reactants minus products. Part of the reason is that all of the bond energies are positive, and the energy of reactants or energy of reaction are not always positive. So we need to make sure that we get the correct sign convention with our thermodynamics. So reactants minus products. Okay, so let's see. I know this is worked over here somewhere. Okay, so this is our general equation for finding enthalpy of formation with bonds. Just a couple of things to say here. You guys all know what this is. That's sum, or sigma. D is commonly used for bond energy. That's what that D is. So notice here, these are our HF bond or FF bond, and then 2 times the HF bonds. And then it's reactants minus products. And then your final answer is probably going to be in kilojoules. I think most of those bond energies are in kilojoules. So that's what we're doing here. Again, looking at the number of moles we have of each of those, incorporating that, showing your work with your units, etc. And then what we've done with those bond energies is found the delta H of reaction. Okay. Something else about bond energy and finding the enthalpy of reaction with that is, just like we saw in that other problem, they may, let me see if I've got another example here. We've got one. This is the formation of freon. Okay, so here's our equation. You're going to have to find all of the Lewis structures for these substances. Figure out what kind of bonding is going on. You might have some double or triple bonds going on in there. You got to use the right bond energy. Then again, if you've got carbon dioxide, make sure you use the correct, I think it's 799 kilojoules per mole for the carbon dioxide. and then take into account how many moles you have of each of those species, and then its reactants minus products, okay, which we've got written here. And then you can find the delta H for that. However, some problems may give you the delta H and all of these. They'll give you this one, this one, this one, that one, and that one. And then they say find the energy of that molecule. And so it's just a simple algebra problem, okay, just like we were talking about before. So sometimes they like to put a little spin on that, where you then would have the total and you subtract or add all of these from that total, depending on what the algebra tells you to do, and then you can solve for that unknown. Wow. 40 minutes, that's what I wanted to be. So you can look through that example in your textbook there. I hope that clarifies some of the other issues you may have been having. Some of you may not have had any issues at all, and good for you. I'm glad that it goes well for you. That's it. We'll pick up on Monday or Tuesday tomorrow. Again, work those same problems I assigned over the weekend, and then we'll do vocab tomorrow. Hey, you guys have a great day, and I hope you don't have to spend all day doing homework. Take care. We'll see you later.